Good morning, everybody. Welcome to another Advent of Code stream. I'm going to change my plans a little bit, and basically, I'm going to try to get 23, 24, and 25 part ones done, and get that done today. Hopefully, day 21, part one, that in and of itself looked like kind of a mind bender. So I've held off on that, but I want to get all the part ones done. And, I have off today because it's Martin Luther King Jr. day today, which that is a good thing to celebrate. King was a great person and did a lot of great things. And that sounds so trite, but that condenses the life of a person and all the people that he influenced down into a very, very small statement. I actually, when I was in college, I had a book that had all of I don't know if it's all, but I think it was most of the letters that he wrote. Obviously a letter from a Birmingham jail, and it was in there among others. And it was just really, really interesting to read. All the things that that he had written in his life, all the letters he has written, and unfortunately, I can't find that book anymore. I don't know where it went. When my wife and I moved up to Minnesota, we lived in a townhome for about 6 months, and there was a room that we just that was before we had kids, and so we just had kind of almost like a spare room. And so we threw a bunch of stuff in there because the plan was to get a house. And so we kind of unpacked all that we needed, but not everything. And so we left a whole bunch of stuff in there. And unfortunately, it was up against a wall, and that wall started to get water seepage. And some of the books I had got damaged. So I don't remember if that was one of them or not, but I can't find it. Of course, I have way too many books, but the books that I've read, I know where they are. And I've looked through that area repeatedly, and I cannot find it, which is kind of sad because I do have good memories of that book. But in any event, I have off today because of Martin Luther King Jr. Day today. And so I thought, I'm going to try to also relax a little bit. I may probably will play some Splinter Cell this afternoon, but I got a couple things to do around the house. So I figured let's not stress myself out too much. Let's just hopefully try to do the part ones and at least pick off most of those other than 21. So with that said, and we need something good to celebrate today. Yes, I'm only talking about the good stuff today. That is it. All right, so let's get some music going and look at day 23. LAN party. I've been to some LAN parties. Sorry, I'm going down memory lane a lot, but just that phrase. When Halo first came out, and even with Halo 2, because you could play that online, me and a bunch of people would get together, I think with Halo 2, Halo 3. I think that was it, though. But we get together probably like once or twice a year and go to somebody's house and just set up a whole network and TVs and playing Halo together in a house. And it was so much fun. It was just a lot of fun. All right. Anyway, enough with nostalgia. As the historians wander around a secure area at Easter Bunny headquarters, you come across posters for a LAN party scheduled for today. Maybe you can find it. You connect to a nearby data link port and download a map of the local network, your puzzle input. The network map provides a list of every connection between two computers. For example, each line of text, actually, hold on, let me pause this. Each line of text in the network map represents a single connection. The line KH-TC represents a connection between the computer named KH and computer named TC. One of the things I've been doing with these problems is I'm also trying to guess where it's going to go, like what data structure or algorithm is it trying to hint at, or basically is based on. Anyway, connections are directional, so they're bidirectional. LAN parties typically involve multiplayer games, so maybe you can locate it by finding groups of connected computers. Start by looking for sets of 3 computers where each computer in the set is connected to the other two computers. In this example, there are 12 such sets of 3 interconnected computers. So AQ, CG, and YN. No, not the link of my. There we go. So you basically need to find a ring. So you found AQ, and then here's the CG. Nope. And then YN. And there's a CG. So basically you have to say, find all the connections. Yippee. In this example, there's 12 such sets of 3 interconnected computers. If the chief historian is here and he's at the LAN party, it would be best to know that right away. You're pretty sure his computer name starts with T, so consider only sets of 3 computers where at least one computer name starts with a T. Find all the sets of 3 interlinked computers. How many contain at least one computer with a name that starts with T? Well, I have a long list. Save as 23. Day 23. Input. So we can ignore things like this and this and this and this because they don't start with a T. None of this stuff starts with T, so that narrows it down a lot. I mean, somewhat. If we look at the input again, like, and it's not just, you can't just look for a T in the string. It's got to, the computer name has to start with a T. So a lot of these just go away. So let's play with this a little bit. Let's clear everything out. And let's do solution day 23. So the first thing I want to just see is, you know, we have to figure out the ring. We have to figure out what the connection is, if there is one. But we probably don't need that. Let's just get rid of this. How many lines are in the file? Over 3,000. Okay, but we can potentially pick these apart. So basically a connection is these, and they're bidirectional. It doesn't matter. There's just a like a node left and a node right, but they don't have, like, the connection goes both ways. So can't totally ignore these lines though, because we have Daniel, just hold up on stuff like that, okay? Please. Okay, I'll read this one, but hold off on stuff like that, even if I fail, okay? We can't totally ignore those lines, though, because if we have TAAY and TABG, it's important to know whether or not your data has an AYBG. I don't understand that. I mean, if you had an AYBG, you would definitely keep that one for consideration. But like this one, oh, I'm sorry. Wait a minute. Let me reverse that. This one you would keep because that has the ability to. Oh, I see what you're saying. Okay. All right. Never mind that. That's actually not. Okay, but from now on, Daniel, please don't do that. Okay. So, in any event, all right. So we can't do that. That's right. How do you do this in the smart way? Parsing it is simple. I mean, you just look for this. Here's a node connected to this node. I guess you could parse all this, look at this one, and say, okay, find me a node. So we have this concept of a public sealed record, a computer, and that's just a string is the name of the computer. Okay, and then we have a public sealed record connection, where this is a computer left and a computer right. Right? And so we could get a list of these, and we could say for each one, this feels brute force and bad. But we could say, okay, for this one, are there any nodes? Are there any connections that are not this connection and have either the left or right equal to this? That either have the left equal to this. Oh, but yeah, you can't. Like if you connected here, then you have to do another search to say, find another one where it's not these two, and this one is either the right or left, and then the other one. So if like we go here and we see a Q, I think I can do a brute force way, but again, brute force is not the way to do this with advent of code. But let's just at least parse the damn input. Okay, so let's say var connections is equal to a new list of connections. No connections. And then for each var input, no, line in input, but we want to split on a dash. And then connections dot add a new connection, new computer, line parts of 0. We're just going to assume that this parse is correct. Okay. This should be fairly quick to do. So we get all the lines and the parts and the connections. Okay. let's just return this for now. Let's scaffold out the testing stuff. And so our input is this. And we want to say for 23, part 1, there should be 7. Which just won't be true because we're just getting the line count essentially right now. Yeah, 32, that looks... Ballpark, that looks right. I saw a Reddit post where someone claimed to have brute force part 2 of Day 20. Well, I can't see 21 just yet. Well, I can't see part 2 because I even just passed on part 1. But if part 1 is hard enough, part 2 I can't imagine. With a few hours on a GPU farm, jeez. Yeah. If there's one thing I've learned about Random.Code, and I mean, really, it's a lesson about a lot of stuff is, and this again is inspiring me to, I've got so many books on like data structures and algorithms and stuff, is to figure out better ways of solving stuff. Because brute force, the Random.Code typically shows that brute force is not the way to go. But anyway, let's move on. So we got this. So we want to say, like, I know this is wrong. What I'm about to do, I know is wrong in the sense of it's going to be too slow. What would we call this? We could say like var 3 sets is equal to a new list. What? 3 sets sounds so stupid. But whatever. Public sealed record. 3 sets. Computer 1. Computer 2. Come on, you can do it. Nope. It doesn't really matter the order. Oh, day 17. I don't remember what 17 was. Oh, this one, yeah. Yeah, I've got to come back to this one. I did, and it's in my notes. And I know some of it is probably garbage and wrong, but I did figure out that you need that many executions. And so this is the first number that does 128 executions or instructions. And this is the last one that does it. That was just playing with a binary, manual binary search to get it down to, okay, that's the range. Obviously, that is well over 200 trillion possibilities in there. So you can't. I mean, you just... going through every single one would be a nightmare. And so there's something to look at here to go, how do you actually... And I was trying to do it, and again, I don't think my notes are right. Doesn't matter. I don't want to get distracted because... I said I would come back to that later. But that one I just kind of went, there's something hidden within the pattern of what you're trying to produce. And you have to kind of figure out how to reverse engineer it in a way. So anyway, all right, let's get back to the problem. I don't want to get distracted here. So we got 3 sets. So now if I said for each connection and connections, thank you, computer. How do I want to do this? So we want to find a connection where it's not our connection and left equals our connection dot left, or the thing on the right is equal to. So I'm just trying to say, let's look at our left node and let's try to find all the connections where one of them is equal to our left node. Okay. We don't care which one. We just want to say, is there a connection? And then for each var complete connection, and I might be able to wrap this up in one big link, but I don't know. Can you iterate within an iteration? We're going to find out. Okay, so... Oh, I'm sorry, in left connections. So now we want to say var complete connections. Excuse me. It's something within connections where it is not equal to no, wait a minute. I'm sorry. The left connection gets you a connection that either has the left or the right matching the left. Okay. So this has to be, I'm sorry, I'm getting ahead of myself. The left connection, we want to find a connection where it doesn't equal the left one and it does not equal the connection we're looking at. So it cannot equal that and it cannot equal that. And that connection's left must equal the connection on the right, or the connection on the right must equal the connection on the right. I think that makes sense. I'll come back to this. Okay. So we'll say complete connections. And now we say for each of our complete connection in complete connections, I'm trying to figure out, so you need at least one of this connects to this, which connects to this, and this would connect back to this on the left. And then we want to do this on the right as well. I think this is right, but I'm going to have to go through this again. And then you have to do this for the right side and say if the right is equal to the connections left or the connections right. Yeah, so basically you'd flip this to that. And a connection goes either way. So it's not like one or the other. I'm just saying left or right, but be nice to do this in one search. But I don't think you can. Anyway, let's just keep moving. This will get me all the connections where it's left or it's right matches our left. So then we get this. And so now that's another node. So we had the connection we're looking at. We're saying its left side matches one of the nodes on this one. Okay. And now, so we know that this two, like that one connects on one or the other. So now we need to say that, because what I'm trying to say is, take some notes here. Maybe I can express it better if I can actually mumble something out. Part 1. So we have X and Y. And what I'm trying to find is something that, for example, has X, Z. Okay. Or it could be Z, X. And then for that one, what we want to find is a connection that doesn't equal either one of these two, but has a left or right that's equal to Y, and the other one needs to be the other's right. So that's what we're missing here. And so we're saying that its left is equal to the original connection's right, and its right is equal to the left connection's right. Or it's the reverse, Z, Y. Its right is connected to the right, and its left is equal to the left connection's right. There. That gives you a complete connection. In that this one connects to left, left connects to complete. Now what we could do is say var 3 connection is equal to a new hash set of string. Does a hash set of string allow you to do something like... It does. Good. The reason why is because I want to say left. I want to say connection left, connection right, except the name now we know that we don't care. This is awful. I'm a horrible person for doing this, but whatever. So that basically says, okay, give me the 3. You know. And then we can say if 3 set any starts with a T, then we can add this into a 3 set, right? But we don't really care about I thought there was a sorted hash set. Sorry, I'm forgetting. Sorted set. Of course. And so we're always going to make sure that the order follows, because we don't want to add in a can't type. And you can't index into a sorted set, can you? Can't span it either, really? Fine. Actually, now we could say it's a dash, right? And we could just say here, can you do this? There. Okay. And then we return the number of 3 sets we found. That failed miserably. I got 33. How do we get 33 out of that? Well, for one thing, we're not doing the other side. I forgot about that. But that's obviously wrong what I'm doing. Let's put in a big to-do here. No, we don't want day 17. We want day 23. Okay, so we get a connection. And I mean, we could even get rid of the computer part. That's kind of useless. So a left connection, this says KH, right? Well, that's right. And now we need to find a complete connection. But that's wrong. We got KHTC, KHQP, KHT. That's wrong. It needs to. I didn't do that connection right. Okay. So to find a complete connection, in all the connections, we want to find another connection that does not equal the left and does not equal the connection, the two parts we found, but its left is equal to our original's right, and then its right this part is wrong. We're saying we want to find where its left is equal to our original's right, or its right is equal to our original's right, but then the other part has to be equal to if the left connection was equal to the left, then we want its right to be equal to the right. So we're saying in this case, it's left here let's flip these around just for my own sanity. Its left here is equal to the original's right, and that means its right has to be equal to which side did you not pair on to here, because this one connects to either one or the other, but you don't know when you're doing this query just yet which one you want to say. So if the left connects to the right has to connect to the right side, the correct side of this middle one. So we're going to say here, if the left connections left is equal to the connections left, then this right we want to connect to left connection right. Otherwise, left connection left. Or in this case, it would be this. So now we found that our right side is equal to the original's right, and so now we need to say the left side is if the left connection equaled the left equal the left, we want you to look at the right, otherwise the left. So yeah, it's just you're flipping around the nodes. Now this shouldn't match, but it should be, oh, it did. Oh, that's right. I don't think you do. I don't think you need to do another pass because because they flip. I'm not sure about that. I'm not sure. This gives me the right answer, but I'm not sure it's right. And that's, in advent of code speak, that's not a good place to be in. But I'm kind of thinking this makes sense because when you get down to a complete connection, that's basically saying that something connected to the right side here. So you close the loop. Did it really matter that if you would have started from the right, you would have found that middle node and you would have found this node again anyway? It's just the ordering would have been different. It would have washed out here and you're fine. I don't know. Let's just see if this actually even remotely works. Confidence is not feeling high on this one, but we'll see. And I have no idea if it's going to solve in any remote sense of completeness. Well, not too shabby, but I don't know if that's right. Hey! Hey! And there was much rejoicing. Woot. Okay. I'm going to quickly look at 20... No. Should I? No. Maybe. I don't know. Let's at least check this in. All right. And I've been missing part 1 of day 23 is complete. And there's other work. I just don't remember what I committed at that point. All right, cool. So that's 23. Okay, I will read it, but I'm going to move right to 24. I just want to see what it is. There's still way too many results to go through them all. You'll have to find the LAN party another way and go there yourself. Since it doesn't seem like any employees are around, you figure they must all be at the LAN party. If that's true, the LAN party will be the largest set of computers that are all connected to each other. That is, for every computer at the LAN party, that computer will have a connection to every other computer at the LAN party. In the above example, the largest set of computers that are all connected to each other is made up of Kodi Kata. I probably said something in a language that's very offensive and I didn't realize it. Each computer in the set has connection to every other computer in the set. The LAN party poster says that the password to get in the LAN party is the name of every computer at the LAN party sorted alphabetically, then joined together with commas. In this example, the password would be that. What is the password to get in the LAN party? What font am I using? That's Cascadia Code. I get that a lot when I do talks at conferences. People are like, "How do you get that ligature?" It's Cascadia Code. And so what Daniel's asking about is if I do something where I say like var x is equal to 3 less than or equal to 4. You notice how the equal here, less than or equal to, and it's funny, let me zoom in because you can actually see it. I never noticed this, but if I start highlighting it, you notice how it half highlighted it? It's because it's actually 2 characters. And then if I do that, so you can see that it does that. That's like a TypeScript thing. But 3 equals, and then if I do, highlighting, it does each character at once, but it kind of combines it into a ligature where it all gets combined. Another one is not equal to like that, and others. So yeah, I like it. It's a nice font, but when I present at conferences, sometimes I get people asking, what new C# symbol is that? I can't find that on my computer or whatever. And then I have to kind of explain, what that is. It will also do it for ellipses, ... It actually combines them sort of together. It's subtle, but it happens. But yeah, that's what the font does. Kokatas. A kata is a simple practice. Yeah. It's funny now that so little exercises that you do to practice coding is kokatas. Yeah. This is funny that you mentioned that because I'm going to turn the music back on. I'm not even going to attempt this one. I'm going to get back to the calendar and we're going to do 24. But when you say katas, I never understood what that is because I've never did self-defense. I've been doing self-defense now for 4 years, 4.5 years. I started in June of 2020. My older son had been doing it for a little bit longer. And he'd always been bugging me to hear, now and again, he'd be like, you should start doing this, Dad. And I'd kind of be like, nah, this is your thing. But it would kind of ruminate in the back of my head. Part of it was I was a consultant. And while I didn't travel a lot, there was always the possibility that I might need to travel somewhere. Which in retrospect, I think there was only like 2 or 3 gigs in my entire 20 years at Magenic. That was the company I worked at. And then I worked at a couple of consulting companies before that. I never did any traveling with other companies. With Magenic, I had to do it for like where I would go like every week or every other week. Only 2 times. And even those were not like long gigs. So, but I was always like, well, I don't want to have to not show up for a week or 2 or a month, But then when I joined Rocket Mortgage, I knew that, COVID, but I also knew that I wasn't going to be probably traveling as much. So I decided, I'll start. And it's worked out. And the reason I bring all this up is because there are these things called katas. There's pinions, there's katas, there's pinions, katas. I'm just blanking. Kempos. We also have these defense techniques. There's also some other kind of forms. There's one called north side and there's one called south side, and those two actually you can do them individually, but you can do them together, and they are meant to work together. There's stature of the crane. So yeah, and all those are basically like karate dance routines. That's the way I look at them. And I don't mean to dismiss them. It's just, there's a specific set of, you have to do this, then this, then this. And it's a lot to memorize and a lot to do. But yeah, that's what a kata is. So now I put those two together. So anyway, all right, let's look at 24. Now let's pause the music. Excuse me. Cross wires. You and the historians arrive at the edge of a large grove somewhere in the jungle. After the last incident, the elves installed a small device that monitors the fruit. While the historians search the grove, one of them asks if you can take a look at the monitoring device. Apparently, it's been malfunctioning recently. The device seems to be trying to produce a number through some Boolean logic gates. Each gate has 2 inputs and 1 output. The gates all operate on values that are either true and false. And gates, yes, this is one thing I was very happy with getting a degree in electrical engineering is I actually had to take a course. It wasn't on like binary logic, like from a philosophical standpoint, but it was basically like this. We learned about and, or, XOR, NAND, NOT, all the different gates, how you combine them, all that stuff. So even though I sometimes really screw up on Boolean logic, but anyway, so AND gates, yes. OR gates is one or the other. XOR is one or the other, but not both. Gates wait until both inputs are received before producing output. Wires can carry 0, 1, or no value at all. Great. There are no loops. Once a gate has determined its output, the output will not change until the whole system is reset. Each wire is connected to at most one gate output, but can be connected to many gate inputs. Rather than risk getting shocked while tinkering with the live system, you write down all the gate connections and initial wire values, your puzzle input, so you can consider them in relatively safety. For example, because gates wait for input, some wires need to start with a value as inputs to the entire system. The first section specifies these values. For example, X001 means that the wire named that starts with the value 1, as if a gate is already outputting that value onto the wire. The second section lists all the gates and the wires connected to them. For example, that and that, 0, describes an instance of an AND gate, which has wires that and that connected to its inputs and which will write its output to wire that. In this example, simulating these gates eventually causes 0 to appear on wire 0, 0, 0, because X0 and Y0, they're 1, 0, so that would be 0. X01 is 1, Y01, 1, so that would be 0. And a Y, X02, which is 1, so that immediately makes it 1. Okay. Ultimately, the system is trying to produce a number by combining the bits on all wires starting with Z. Z is the least significant bit, then Z0, Z1, and so on. In this example, the 3 output bits from the binary number form... Yes, okay, I see what it's saying, which is equal to the decimal 4. Here's a larger example. Oh, God. Well, I guess you could go through this and say, just keep iterating until you can't iterate anymore. Like you figured everything out. So if the first pass would say, do I know what this is or this is? This is where the nullability or not value comes in. We could say, is it -1? Because we don't know what it is yet. If either of these are unknown, then we don't do it yet. This one, oh, we do know what this one is, and we know what this one is. So now we know what this one is. Okay. This one we don't, this one we do, so we could figure out that one. And then we go through each one, and there may be, do they do something where they eventually, like, do they ever have one in here that, well, not on the example. Like this one is a simple one because we can use this as the input because there are no hidden or extra variables. This one we do, so we have to basically generalize to say these are our inputs, these are our variables. If we basically run into a variable that we've never seen before, we add it to our list with the initial value of 1. If we run into a variable but we don't know what it is yet, because maybe that's not the case here. Actually, yeah. So when we pass through this the first time, we'll see that we don't have these two or this one. So we'll make those variables with initial values of -1, I'm sorry. When we get down to here, we could do it. We're not going to come back up here and try to do it because we're just going to keep iterating until we have solved everything. We never ran into a new variable or a variable that doesn't have a value. And something like that. And so here we could solve FGS and put that in. So the next time we come through, if we say, now let's go find NTG, well, we might be able to do it depending on was this solved or not, you know. But this will solve this one up here. So at least we'll have that ability to do that. And so I think you just have to you got to keep iterating because there has to eventually go to a solution, right? So let's keep going. Big input. Huge input. And so, yeah, eventually we're going to have to figure out, like, for the Z's. And there is something called a bit, like there's a bit array or something like that in .NET. I think there's like a bit array. Yeah. And just to show this real quick, if I say var bit array is equal to new bit array, so let's just say 32. We really don't know. We don't know how many bits there are, but we have to order them correctly. So let's just say we have 32. Then BA, you can say at index 3, for example, that's either true or false. And so we could set all them. And then I think is there a way to turn I thought there was a way to take a bit array into an integer or something like that. Convert it into a bit array, but we want to go the other way. Oh, bit array copy 2. Oh. Where am I? So we could copy to an int. How many do we have in here? Z30. We do. Do we have 31? Yes. Do we have 32? Yes. Do we have 33? We have 34. So it's going to go past an integer. I don't know how far it's going to go, but it's definitely going to go past that. So that ain't going to work. I mean, the other thing we can do is we can shift in a bit value for all the ones that we're finding. And if we sort them, once we find all the Z's, we'd say basically find Z's sorted by, and if it sorts correctly, then we'll know what their values are, and then we can just shift them into like a big integer or a long. Because a long is 64 and a int 128. We could do int 128 big N 0, and then we could say big N, because that's a shift in, right? Shift a value left by a given amount. And so what we could do is reverse it. We'll go like from the top to the lowest, and we can shift in. Fine. So if we do like 1, 0, 0, 1, and then we just say console right line, big N, and let's just not do that. Let's see what this does. This should be like, I'm closing my eyes because I don't want to see it, 8421, so it should be 9, and it's 0. Of course it's 0. I'm obviously not doing this right. Oh no, I don't want to, I want to shift in a bit. I'm just forgetting how to do this off the top of my head. We'll cross that bridge when I come back to it later, because I know there's a way to do it. I'm just being brain dead right now. So let's make, is this 24? 24. No. Twenty-four. Okay, so if we come back here, did I save this? I don't remember if I saved it. Nope, because I never put in a 24. Day 24 input. Okay, so we basically need to keep parsing until we see a blank line. And once we do that, then we basically need we could parse each equation, because in each equation has like left side operation, right side result. Right? Okay. So we need the concept of a wire. it's really a variable, but string name, because you have x00, ntg, whatever, and it's int. We want a tri-state is what we really want. But we're just going to say value. And we know that we could do a signed byte. I mean, that's going to be the smallest. But bleh, we don't care. We could also make these nullable booleans, but I don't want to go there. Okay. And so what we want is, oh yeah, we also need an equation. A public sealed record equation. String left string. Well, we could have public enum operations, which is XOR, what was it, and or XOR. No, not your. What the hell, really? Actually, let's name it operation. And then string right, string result. Could we as we're building the equations, we could make these wires, which is basically a variable holding a value, and initialize in the 1. The problem is I want the reference here, like NTG, to be the same one that you do down here. So I could keep a list of wires as I'm going through this, and if I don't have it yet as I'm parsing it, I'll put it in the list and then also put it down the equation. If I do have it, then I'll grab that reference. And since these are reference types, they'll always be referring to the same reference. Okay, so now we need to say var split index is equal to the input where index of, and my hopefully intent is that we want to first get wires, and then we want to get equations. And so what we could do here now is say for var w is equal to 0, w is less than split index w plus plus. And we know that these are going to be wire definitions. Okay, so we could say var wire parts is equal to the input at w split on a colon. And then these we know will not exist. So we're okay with saying wires.add a new wire where the name is the wire parts of 0. And then this is int.parse wire parts 1. And yes, culture info, because we got to do that. And we'll just trim that just to make sure. So that will parse. That should be fine. Okay. Now we got to get the equations. So now we want to say for var e is equal to split index plus 1. We want to move past it. E is less than the input length. E plus plus. Okay. And so now we got to do a little bit more. We can split on this token, and that will get us parts is equal to input E split on that. Okay. And now we need our expression parts. Which we can split the first one, equation parts, and we're going to split on a space. That'll give us the 3. Okay. And so we also need var equations. New list of equations. Okay, so var left is going to be if wires contains it's singular to index of I want an index of where I could actually find index. Okay, where the wire is equal to that. I want to say try. Let's do this. Single or default. If left is null, that means we did not have that yet. So we're going to say left is equal to a new wire with expression parts of 0 minus 1. Because we don't have a value for it, and we need to add it back into our wires. So we know that left here at this point it shouldn't bark. It should know that it's not null there. Good compiler. Good compiler. Okay. Let's do the same thing for the right. I'll fix this in a second because it's got to be 2. Var operator is if expression parts 1 is equal to and we have operation and. Else, if this is equal to an or, we have or, otherwise it's got to be that. You don't like it when I do that, do you? Yeah. Because operator is a keyword. Okay. So we get the equations, we get the wires. We're not done here yet. We got to get left, right, operator, and var result. Our result is on the wires where we take the equation parts 1, because that's what's on the right side. If that's null, we do this, and we're going to add it in, except now we have to say equation parts of 1. And we don't have a value for it. And now, equations dot add, new equation, left, operator, right, and result. There. Why don't you like this? Oh, yeah, we need these to be wire left, wire right, wire result. There we go. Okay. So this will get us all the wires, all the variables, all the equations. And so now we just do a while loop until we, how do we do this? We basically while loop until something. Yeah. While true. For each of our equation and equations, what do we want to do here? We want to say if the equation's left dot value is not equal to -1, and that's a start, because if they don't equal that, fine, but the right side may or not be evaluated yet. So if equation dot result value is equal to -1, then we had to do an evaluation. Evaluation occurred, which is equal to false. Of course, I can't spell. And when we come out of this, if we didn't get any evaluation, we break, because now we've got all of the wire values. By the way, if you're new to the channel, if you haven't subscribed, please subscribe. I would greatly appreciate it. I am about 150 subscribers left to 1,000. So that's my first goal. So please subscribe. I would greatly appreciate it. Okay. So if we had to do an evaluation here, we got to say that's true. And now we actually have to evaluate the equation, right? So we need to say, oh, shoot. We can't make these immutable. crap. The reason I say that is because the name is immutable, but the value is obviously going to change. And we can't do withers because that's going to actually change the reference. Right? We were hoping that all of the variables are going to be by reference. If I suddenly change the result on the equation, like if I could say equation.result.value is equal to the operation, that'd be fine because it would still be the same reference everywhere. But as soon as I change that, yeah, I'm gonna have to fortunately make this a class wire, get rid of this, rid of that, and we're basically gonna need two properties: public string name get public and value get and set. I typically don't like to do this now, but needs must. Public wire string name and value. This dot name, this dot value is equal to name value. Okay, now we actually have what we need, which is if we have to get the evaluation, we can say equation result dot value is equal to, well, if no, the equation's operation is equal to XOR. If it's that, no. God, you know, all this AI code completion, all this stuff, sometimes it gets really annoying. It's like, could you just shut up? Let's say and. That's going to be equation left value and equation right value. Yes, I'm getting there. If it's an OR, then we do an OR. Otherwise, the only other thing it could possibly be is an XOR. So let's actually make sure we're doing an XOR. I wish it would tell you here, like, what operation that actually is, because I'm just always used to, like, upper caret. I know it's an XOR, but I just wish it would actually tell you what it is. Like, I know that's a bitwise and, this is a bitwise or, blah-de-blah-de-blah. Okay. All right, so now we got our value for this. Otherwise, if we don't know what one or the other is, we can't evaluate this. And so this is not right. What I want to say is, like, if I just do this for one, that's wrong. What I want to do is basically say, if no evaluations occurred, which we would have here. Yeah, so I think that's right. Talk about binary logic. I think that's right. I think that's saying if we get to the point where an equation has a left value and a right value and the result was evaluated, we skip it But we're going to be evaluating for a while until we get to the point where everything's evaluated and then we break out. And so now what we need to do is get a sorted list of wires where the starting character is a Z. Z wires, which is equal to, excuse me, sorry. For each var Z wire in wires where starts with a Z, order by the name. Okay. Now we need to shift these bits in. So that should be a long. Oh, what are they calling this? We'll call it the system number for lack of a better idea. Yeah, you know, languages are not always consistent in how they handle that stuff, which is great. It's great. Okay, so we get all the Z wires. Hopefully they'll be in order. And now we need to, we want to push them in. And now it's going to tell me is a compound, but that's not what I want. What I want to do is shift in that value and so I want to keep shifting bits in. So how do we... I'm just being stupid. I know there's a way to do this. Shift bit. Yeah, I get it. It's shifting it over, but that's not what I want. I want to shift a bit in. Oh, I just... Sorry. We want to shift it over one bit, and a 0 will just shift to 0. And then we say system number or equals bitwise OR operator use an assign extended operand. What? There, shut up. Fine, shut up. Like I said, Daniel, if I want a hint, I'll ask for a hint. Okay. I knew that there was a way to do it. It just was taking me a second to get there. So. All right. So I guess the only way to know is to run. So let's run and see how bad off we are. All right, so let's grab the input from the sample helper. So this one is small. For a second I thought I heard my cat scratching at my door. Sometimes he likes to come in, but whatever. Okay. So let's say part 1's small. Because that's perfectly valid. It's perfectly valid. We just don't have any so in this case it should be 4. And then for the part 1 larger test, that's this one. Which just is more ugh, come on. This is a little bit more realistic as to what we're actually going to be dealing with. And this should be 2024, because of course it should be 2024. Let's do the small one first and see what happens. Failed. I got 0. Yay! Yippee! I mean, there could be all sorts of wrongness in this. So, do we have any wires? We have 9 wires. Z02 is 1, Z01 is 0, and Z00 is 0. So actually, we did get the right answers. Because it said 02. Gets a 1, a 0, and a 0. Okay, now it's just a matter of, does this ordering work? How did it not get any? What? So, that doesn't make any sense. Index of Z is equal to 0. None? What? Its name, it looks like it's starting with a Z to me. What in the world? Wires where its name index of z equals 0 or starts with z. How are they coming back with 0? This is really confusing me. How do you get... If I said wires at 8, name... Oh, they got fucking spaces. Sorry, language. It was hard to see that space in there. I was missing the space, so... Okay, so we'll just come back up here and do a bunch of trims. That's interesting. Because we're splitting on that. Why would it have put a... Well, now I'm paranoid. Can you... Trim entries. Thank you. I remembered in the back of my head that as I'm doing this, I'm like, wait a minute. No. There's a way to say automatically trim everything so you don't need to do it yourself. Nope, we don't have any more. Good. Okay. So for whatever reason... Oh, I know why. Because it put the space here when we're grabbing the variable or the wire. That's why these don't, because they don't start that way. But now we'll be consistent because we trim all the entries. What do we get now? Still a failure. Oh, you didn't get a 0. So now we should get a Z wire. And that's... Oh, order by descending. That's why. Because we want the most significant bit in to get in first because we're going to be pushing it over. Now that passes. And now that passes. Okay. Let's do 24. Twenty-four. Whoops, no, not comment. What does that do? Wasn't too slow, but let's see if that's right. Hey! Hey! We got a winner chicken dinner. All right, get commit. Part 1 of day 24 is complete. Let's just take a look at 2 real quick and see what madness lies in with that. After inspecting, turn the music off a little bit. After inspecting the monitoring device more closely, you determine that the system you're simulating is trying to add 2 binary numbers. Specifically, it is treating the bits on wires starting with X as one binary number, treating the bits with wires starting with Y as a second binary number, and then attempting to add those two numbers together. The output of this operation is produced as a binary number in the wires starting with Z. Now three places, wire 0, 0 is same for 0. Okay. The initial values for the wires in your puzzle input represent just one instance of a pair of numbers that sum to the wrong value. Ultimately, any two binary numbers provided as input should be handled correctly. That is, for any combination of bits on wires starting with X and wires starting with Y, the sum of the two numbers these bits represent should be produced as a binary number on the wires starting with Z. For example, if you have an addition system with 4 wires, with 4X, 4Y, and 5Z wires, you should be able to supply any 4-bit number on the X wires, any 4-bit number on the Y numbers, some of the two numbers as a 5-bit number on the Z wires. One of the many ways you could provide this in such a system, pass 11 on the wires, X, 13 on the Y. If the system were working correctly, then after all the gates are finished processing, you should find 24. (11 plus 13) on the Z wires is the 5-bit binary number that. Unfortunately, the actual system needs to add numbers with many more bits and therefore has many more wires. Based on forensic analysis of scuff marks and scratches on the device, you can tell that there are exactly 4 pairs of gates whose output wires have been swapped. A gate can only be in at most one such pair. No gate's outputs were swapped. The hell? For example, the system below is supposed to find the bitwise AND of the 6-bit number on 0 through 5 and the 6-bit number on Y, and then write the result as a 6-bit number on Z through 5. However, as an example, 2 pairs of gates have their output wires swapped, causing the system to produce wrong answers. The first pair of gates with swapped outputs is that and that. The second pair of gates is that and that. Correcting these two swapped results in the system that works as intended for any set of initial values on the wires that start with X or Y. In this example, 2 pairs of gates have outputs that are involved in a swap. By sorting their outputs wires names and joining them with commas, the list of wires involved in swaps is this. Of course, your actual system and the gates that need their output swap could be anywhere, not just attached to the wire starting with Z. If you determine that you need to swap out wires A with E, 0 with that, system of gates and wires have 4 pairs of gates which need their output wires swapped, 8 wires in total. Jesus, I'm skipping over that one. I don't even quite understand what the hell I was just saying. Yeah, I'm just going to go right to 25 because that made absolutely no sense whatsoever. But before I do 25, I put the music back on and we'll put that as the background. I do need to take a little bit of a break here real quick. So it's 10:55. We'll say 11 o'clock-ish. So I will be back. If you're watching and you haven't subscribed yet, please subscribe. I greatly appreciate it. But I won't be gone for too long. So just give me a couple minutes, fill coffee, hit the bathroom, and I will be right back. Okay, I'm back. Yeah, it doesn't surprise me about the day 24. That second part just, and I was thinking about this too. There's goals and then there's realism. And if some of these part twos just simply get to be too much, I don't want hints. I don't want to be told what it is. I might just say, you know what? This is about as best as I could get, and I'm just going to stop there. I'm not doing that yet. Because part of it is the fun of trying. But there's also the realism of I have a life, I have a job, I have things to do, and I can't be spending a lot more time on this. So we'll see how far I get. So I would at least like to get all the part ones done. But some of the part twos, I might just be going, I might do those off camera and just kind of do them on my own time and say, this is what I'm going to do for the streams. We'll see. I don't like putting a goal out there and then not hitting it, but again, there is reality to this. And, I have a family, I have a job, I have hobbies, I have other things, and man, trying to get all this done would be a fair amount of work. There were some like in 2022 that I think there was like one problem that I went, if you don't know the trick, you're never going to solve it. There's just no way that you will ever solve it. It would take way too long. But it was just fortunate that I knew that trick and then you could solve it. And so that's another thing about having a code is, the level of difficulty and how do you look up what you're trying to accomplish without inadvertently stumbling across the answer, So, time itself is finite. That is very true. So, all right, let's move on to the last day, part 1, and pause the music, and we'll see what this does. Out of ideas and time, the historians agree that they should go back to check the chief historian's office one last time, just in case he went back there without you noticing. When you get there, you're surprised to discover that the door to his office is locked. You can hear someone inside, but knocking yields no response. The locks on this floor, are all fancy, expensive virtual versions of 5-pin tumbler locks. So you contact North Pole Security to see if they can help open the doors. Unfortunately, they lost track of which locks are installed and which keys go with them, so the best they can do is send over schematics of every lock and every key on the floor you're on, your puzzle input. The schematics are in a cryptic file format, but they do contain manufacturer information, so you look up their support number. Our virtual 5-pin tumbler product? That's our most expensive model, way more secure than you explain that you need to open a door and don't have a lot of time. Well, you can't know whether key opens the lock without actually trying the key in the lock due to quantum hidden variables, of course. But you can rule out some of the key lock combinations. The virtual system is complicated, but part of it really is a crude simulation of a 5-pin tumbler lock, mostly for marketing reasons. If you look at the schematics, you can figure out whether a key could possibly fit in a lock. He transmits some examples. I'm assuming those are the 5 pins that go down. If you've been watching me place, or they go up. I don't know. The locks are schematics that have their top row filled and the bottom row empty. The keys have the top row empty and the bottom row filled. If you look closely, you'll see that each schematic is actually a set of columns of various heights, either extending downward from the top for locks or upward from the bottom for keys. For locks, those are the pins themselves. Yep, you can convert the pins in schematics to a list of heights, one per column. For keys, the columns make up the shapes of the keys where it aligns with the pins. Those can also be converted to a list of heights. So you could say the first lock has pins height 0, 5, 3, 4, 3, right? Or that the first key has heights 1, 2, 3, 4, 5, 0, 2, 1, 3. Okay. These seem like they should fit together. In the first 4 columns, the pins and keys don't overlap. The key cannot be for this lock. The rightmost column, the lock's pin overlaps with the key, which you know because in that column, the sum of the lock height and key height is more than the available space, right? So anyway, you can narrow down the keys you need to try to check. You need to try by just testing each key with each lock, which means you would have to check, wait, you have how many locks? But the only installation that size is at the north, you disconnect the call. In this example, converting both locks to pin heights produces, converting all 3 keys to height produces that. Then you can try every key with every lock. Lock that and lock that, overlap in the last column. All columns fit. So that's interesting. Because if they're saying lock 0 and all columns fit, it doesn't have to fit perfectly, if I'm understanding this right. Because this one is saying it's a 3, that's a 0, and that fits. It doesn't fit perfectly, but it fits. So you can get all the locks, you get all the keys, and yes, it's a very brute force search, but it doesn't seem like a lot of them. And then you just need to look at, for each lock, look at a key, and then at each position, does the addition go over 5? And so as you're parsing the file, you would parse by saying, if I hit an empty line, then I'm going to do something else. Right? Now, is he ever a bastard? Which is saying that the entire thing would be blocked off. I don't think you could, because it'd be 1, 2, 3, 4, 5. You'd have 6. You'd never do that. So if the first row is all things, then it's a lock. Otherwise, it's going to be a key. So you can look at that pattern and then process it accordingly. So I don't think this will be too hard. I don't want to curse myself, but yeah. Let's see what happens. Let's get our 25 in. We get our input. Clear all that out. Get rid of these. So we could get keys and locks. Both of them are basically the same thing, but it'd be nice to have, different types for those. It's how you parse it is what matters. So we could just say public sealed record. A key, we could have not a short. Might be a short. We could just make it an int and whatever. I'm thinking. We could just say int height 0, int height 1, int height 2. How many are there? 1, 2, 3. There's 5. Int height 3. Int height 4. And then we could have sealed record lock, which is basically heights too. You could look at them that way. And then what we want is something that's going to say private static read only. No. It's going to be a mutable array of keys and an immutable array of locks. Parse input. And so we're going to say var keys locks are equal to solution day 25 parse input input. Okay. Var fits is equal to, we're just going to make this an int for now, is 0 return fits. How many fits did we get? Okay. And so we're going to say for each var lock in locks, oh, that's a keyword. For each var key and keys, we'll do an evaluation and then we'll just add up fits. Okay. So we're going to have for var I is equal to 0, bleh. We could say static key parse key given the input and the index of where we're going to start parsing. And then we'll also have something here to say parcel lock. So now what we need to do is say oh, that's got to be a lock. If input at I is equal to that, right? Whoops. That. Whoops. That. That is a key. So we need var keys is equal to new list of keys. And var locks is equal to a new set of locks. And eventually we're going to return keys and locks. There. So this is keys.add, parse a key at that index. Else if input I'm going to do something a little risky here, because we know as we start, we're going to see either a key or a lock. It's not going to be a blank line. So we're going to say else locks add a lock. Okay. But now we got to increment I like by 6. What do you actually have to increment it by? So if we start here, we're on this line. So we need to say we're going to go we need to get 0, 1, 2, 3, 4, 5, 6, 7, 8. We need to actually get 8. Because we're on index 0. 2, 3, 4, 5, 6. We need to get to 8. Now, if we're on the last one here, and we say 1, 2, 3, 4, 5, 6, 7, 8, we'll do that but we'll fall out of the for loop. We won't over-index the array. And so now for a key, what we need to do is say there are basically 5 pins down, and for a lock there are 5 things up. And we just need to go through each row and say, at this index, is it a hash? And if it's not, then we don't increment. And we could actually stop, but we'll keep it generalized. So we'll give it +1 here because we know we're going to start. Actually, let's not. Because a key goes down. I'm sorry, a lock goes down. A key goes up. And this is the other way around. A lock is this. A key was where it's at the bottom. So now we need to say for our I is equal to index +1. So for here, we need to go 1, 2, 3, 4, 5. I is less than index +6, I ++. So now we're going to have our height 0 is equal to I thought there was a way. I mean, we could make this a tuple and make them all zeros. There. So as we're going now through each row, at that index, this is going to look awfully ugly, but never stopped me before. If item at 0 is equal to a hash, otherwise it's just the height. Can't destruct a tuple of 6 elements. Fine, fine, fine. It's going to try to be clever, but it can't be. 1, 2, 3, 4. So height 1 will be the items 1 height. 2 will be 2, 2, 2. No. 3, 3, 4, 4, 4, 4. So that should get us all of the, and I know once you start seeing that one won't be, you can basically say stop doing that, but this is just simpler to write it this way. Then we can say return new key. Terrible, terrible guess. You're not getting the hint. Lock. There. And now the key is almost the same thing. Except we're told we're at the top of it, and so we need to actually go down. So again, looking at the problem, we would be given this line. And so we need to go 1, 2, 3, 4, 5, 6. Actually, we could go 5 index. Because we're given this index here. So we need to go 1, 2, 3, 4. But we only go 5 down. And that makes me think with the lock, we want to be less than 6. Because the lock will be given this index here. And so if this was 0, 1, 2, 3, 4, 5, 6. We want it to be less than 6. This, we're given this, so we can go 1, 2, 3, 4, 5. But then we want to be less than or equal to that index plus 1. And we go minus, minus. And so this is a key. I think that's right. This looks like a time for the multi-cursor stuff I sometimes see in my colleagues using. I don't know what multi-cursor is. All right, so we're going to get our keys or locks. We skip over, we get the keys and the locks. Now, we need to say for each lock, we need to go through each key. If lock at height 0 plus key at height 0 is less than 6. That's the max height. So let's so it could be 3, it could be 4, but as long as it's less than, let's make it less than or equal to, because it's got to be 5. That just reads a little bit better to me. And we do for 1, 2, 3, 4. I'll get to that eventually. If it's plus plus. Except we code correctly and we put things in blocks. A little opinionated there, but so now we say 1, 2, 3, 4. 1, 2, 3, 4. Is this right? I have no idea, but ready to give it the old college try. And do they just give us one problem or two? Just one. Okay. So we just have part 1 here. We don't have a small. We could make a small if we wanted to. So 25 is 3. That should be the answer. Is it? Nope. That's okay. That's why we write tests. 4. Well, oh, multi-curse. Yeah, I think actually, yeah, okay, now I know what you're talking about. VS does support it. I just forget what it's like, oh, I see that. Yeah, I see it. It's cool, but I never get around to actually doing it. So, all right, let's kind of walk through this logic and see. We could actually get to here because we know that we should get 2 locks and 3 keys with these values. Oh, I need to actually run the test. We get 4 keys and 1 lock. Because of course we do. And they're all zeros. Wow, I really botched that up, didn't I? But that's okay. God, actually run. Okay, so we get 0. And we should see that that is a lock. So we go into here, we say the index is that. All these are 0. Yes. So we're going to go 1 down. We get the input. So we're going to say height. If it's basically a part of a pin, we're going to add to it, which we shouldn't be because this one should be 0. This one should be 1. That one should be 1, 1. Okay, we get the next one. What? God, why is the debugger doing that? Drives me nuts. Okay, so once again, I'm here to parse a lock. And of course, you just blasted right through it. 5, 3, 4, and 3. Oh, they're down here. Duh, forget that. So we return a new lock. We add to our locks 0, 5, 3, 4, 3. 0, 5, 3, 4, 3. So we should have gotten that. Okay, cool. We now skip. Oh, crap. I went 1 too far. Yeah. Because now we're at 9. And it's just a simple 0, 1, 2, 3, 4, 5, 6, 7. We're going to add 1. We want to go to 8. Off by 1. That's at least one problem. Still fails. Now we get 6. Okay, so now let's see if we get at least all of our keys and locks. 3 keys, 2 locks. That's correct. And if we look at our locks, we have 5, 3, 4, 3, 3. 1, 2, 0, 5, 3. 1, 0, 2, 5, 3. Oops. 1, 2, 0, 5, 3. 1, 2, 0, 5. Okay, we got that right. Keys. Keys are completely messed up. Okay, so we have an issue with the key parsing. Fine, we can focus in on that now. Ah, other way, dummy. There. Okay, doesn't mean we're right, but... Oh, I never grabbed the input. Okay, sorry. Save as day 25. Input. Let's see how off we are. This is 25, and make the file 25. What do we get? Oh, we got to include that. Is that the right answer? That's the right answer. Well, we accomplished the goal for today. So that's good. Git commit. Part 1 of day 25 is complete. Let's take a look at part 2 just real quick. You and the historians crowd into the office, startling the chief historian awake. The historians all take turns looking confused until one asks where he's been for the last few months. I've been right here working on this high priority request from Santa. I think the only time I ever stepped away was about a month ago when I went to grab a cup of coffee. Just then the chief notices the time. Oh no, I'm going to be late. I must have fallen asleep trying to put the finishing touches on this chronicle Santa requested. Yeah, I can already tell. You can't do it. And that just reminded me that in 2022, the 50th star, you need all 49 to even be able to do it. So I'm not going to be able to do this, but let's just keep reading. But now I don't have enough time to go visit the last 50 places on my list and complete the chronicle before Santa leaves. He said he needed it before tonight's sleigh launch. One of the historians holds up the list they've been using this whole time to keep track of where they've been searching. Next to each place you all visited, they checked off that place with a star. How could they request? With all this, we might just have enough time to finish the chronicle. Santa said he wanted to wrap it up with a bow, so I'll call down the wrapping department and, hey, could you bring it up to Santa? You nod, and the historians quickly work to collect their notes and the final set of pages for the chronicle. You don't have enough stars, you need 7 more. Bite me. Okay. Oh well, you can't win them all, but I did get that first part done. I did accomplish what I was looking for. So 21 is abysmal. But I have 42 stars. 42 out of 50 is a... It's a B. It's a B. So really, I can't even consider 20. There is no part 2-ish to 25 just yet. I'd have to do all these to figure it out. This one is a beast. 20. Yeah, that one's also kind of a beast. And trying to figure stuff out. 21, I don't even want to look at 22, the monkey market. This one, I kind of thought about it and I went, I don't know. Because you have to look at everybody else's sequence to see, is there a spot where that pattern exists? But what you'd probably want to do is say if it exists, whether it exists or not, you have to look and say, okay, what would that cost be? So for that pattern, what's the cost? And then then you move over one and you see if it's in the next one. I think maybe the trick is to say, have we already evaluated a sequence? Is it possible? Well, and we probably would want to do that. Like if we come to a next one, and it has a sequence that we already have done, we don't need to do that again. So if we look at what day is that? 22. Come on. How many numbers do we have? We have 1536. So if we look at calc, it's 1536 times. It's 2000, but it's a little bit less than that, a tiny bit less than that, because you can't get all the way. Once you get to the end, you don't have a sequence of 4 anymore. So we'll just say 2000. That's 3 million possible unique sequences. Okay. But is this the case like what we saw with the stones and the other one that I'm forgetting off the top of my head, that if you've already calculated something, you don't need to calculate it again? And I think this problem has the thing of when you calculate a sequence for a given, like the sequence starts at a whatever the cost is or whatever that, like when you do the ones number. You just need to say, did we ever do this sequence before? And if we didn't, then if we haven't done that sequence before, then we have to go through and look at all the other rows and say, where's the first place that this sequence exists if it does? But I think that would make, at most, the first one you're going to go through 2,000 sequences, and you have to look at all the 1,500 to say, does this exist in it? That's not terrible. Because you could abandon the ones. You don't need to know those unless you find, like, you just keep the sequence of all the changes. And so if you find at a certain sequence where that index starts, you could always go back and say regenerate the number, because you know what that's going to be, mod 10, and that'll give you the ones, and then you know what the cost is. So you don't have to keep all the costs around. That does mean that you have to calculate the ones every single time. But to me, it'd be a little bit of a trade-off to say. So this one might be the one I tackle next, because I think it's possible. It's just doing index of, like, on an array. If we can do them as spans, that would be ideal. Because I know we did something as span. And you can say sequence equals on another span. And I believe sequence equals is just generic, and that would exist on any span. Yeah, so that would actually be ideal, because then we could say get a span from here to here. We keep all the changes in an array, which is only going to be 2,000. It's not that big of a deal for every number. And then we just say, well, for the first one, go through that and then, like, grab this chunk as a span and then look through all the other ones to say, well, we don't want sequence equals. That would not be right. We would want index of. Obviously this isn't correct, but I just want to see here real quick. Searches for the specified sequence, returns the index of its first occurrence. Boom, that's exactly what we want. That's exactly what we want. So let's get this out of here before I really break stuff. And that'd be quick because that's not copying arrays. That's making a span on it and trying to find it as quickly as it can. So that might not actually be too bad. I might consider trying to conquer 19 next and do that as a stream. Wait. No, that was the Linux. I'm sorry, was that 20? No, not 20. Not 21. That was 22, right? Yeah, that one might be one I can try. 23, the Lamb Party. That one's also fun because you need to say how far, like what's the longest list, and I can see that being a blow up problem, so I don't have a real answer on that right now. 24. This one I just didn't get my head around this. I could not figure out what it was even trying to say as a problem. So I might do one more stream sometime this week, doing 22. The other ones, I just don't have a clue on as to how to really solve it and not have my computer melt. So yeah, I'll leave this for now. I think 22 is possible with my limited brain capacity, and then that might be it for Random.Code for me for this year. Or at least I'll try to do the rest off camera. So with that, I'm going to now do a workout, and I got to do some stuff, a couple of chores around the house, but then I probably will be doing a Splinter Cell stream, this afternoon and or this evening. So with that, thank you for watching. If you haven't subscribed to the channel yet, please do so. I would greatly appreciate it. Trying to get to 1,000 subscribers as my first milestone. And with that, I will close the stream out. Thank you all for watching. Take care, and I hope to see you in the future.